Hello, my name is Lacinio Souza, and today I want to demonstrate our C-PHY D-PHY combo in TSMC 12 nanometer FinFET technology. What we have here is a state-of-the-art 64 megapixel image sensor configured to operate at 3.5 gigasymbols per second, which is the data rate associated with C-PHY version 1.2. And it is connected to our CD-PHY RX 12 nanometer solution assembled in this board. You can see the 9 SMP connectors that represent the 3 trios, and the actual test chip is right here. The SMP cables are intercepted with this special test probe and connected to a high-frequency scope. So now we change the setup a little bit, and we want to look at the recovered clock in the PPI interface. So the PHY is recovering the C-PHY traffic coming in from the line and takes care of the necessary transformations until we get the bit stream and the associated clock signal in the PPI interface. So here we measure 500 megahertz, which makes sense as we are operating at 3.5 gigasymbols per second. So let me just elaborate here. We have 16 bits per cycle coming out of the PPI interface. In C-PHY mode, in receiving mode, the demapping algorithm implemented under the hood converts a sequence of 7 symbols to 16 bits. So if we multiply 500 by 7, we end up with the 3.5 gigasymbols per second. Our C-PHY in 12 nanometer is able to recover the C-PHY traffic at 3.5 gigasymbols per second per trio. And in this case, the traffic is coming from a real device. We're talking about one of the most advanced image sensors available today. Note that the total bandwidth for the 3 trios is 10.5 gigasymbols per second, which translates to approximately 24 gigabits per second total bandwidth. So since the symbols, each symbol carries approximately 2.28 bits of information. It's one of the interesting things about the C-PHY architecture. Now, switching gears, let's look at the CD-PHY TX. So let's look at the transmitter side. The setup is very simple. We have the same board with the CD-PHY TX test chip. We configure the setup to run at 3.5 gigasymbols per second per lane in C-PHY mode. We exercise the PPI, and we connect directly to the scope. In the scope, we have the official test tool to run the MIPI C-PHY CTS version 1.2, the conformance test specification. We hit the run button to get the report, and we need to wait a little bit. And once we wait, we start getting the eye diagrams they're looking very good, as well as the various parameters that need to be checked as per the CTS spec. As you can see, everything is passing with distinction, which is great. Let's also look at the CD-PHY TX configured in D-PHY mode and operating at 4.5 gigabits per second per lane. So for the 4 lanes, we're talking about 18 gigabits per second total bandwidth. 4.5 gigabits per second per lane is the D-PHY version 2.1 of the spec. So we exercise the PPI, and we run, in this case, we're running a built-in tool for eye diagram analysis in the scope. And here you can see that the data rate is 4.5 gigabits per second. And here it is, the eye diagram that looks very good. So at Synopsys, we guarantee and deliver a high-quality, robust solution for MIPI. And one of the many things we do is actually run all these steps in different voltage and temperature corners to make sure that we have positive results. We did this with the 12 nanometer test chip that I'm showing you here, but we actually also have a 7 nanometer version of this test chip, same architecture in 7 nanometer, and it shows the same behavior. So moving to a different setup, now I want to show you everything working together. Our MIPI CD-PHY RX working with our MIPI CSI2 combo controller that handles the camera protocol. So in this demo, we're capturing an image with the MIPI image sensor, and we're projecting it to a HDMI display. So what we have here is the same 64 megapixel image sensor with 3 trios attached to the CD-PHY RX, which then connects to the CSI2 controller through the PPI interface. The CSI2 controller is implemented in an FPGA in this purple board, together with some additional housekeeping components. For example, it includes a DMA engine that collects the incoming pixel information recovered by the CSI2 controller. The board is connected to a PC via PCIe, where we're running the software drivers and application to configure the entire pipeline and make the necessary transformations to drive the HDMI display. And well, here it is. We're capturing a nice banner that we had sitting here, and we're projecting it on the display. And well, as you can see, our MIPI CSI2 RX solution, composed by the MIPI CD-PHY RX and CSI2 combo controller, is perfectly interoperable with a state-of-the-art 64 megapixel image sensor. This concludes the demonstration of our C-PHY D-PHY combo, which is now available in all advanced FinFET nodes. We're talking about TSMC 16, 12, 7, 6, and 5 nanometer. So if you need more information, please don't hesitate in reaching out to Synopsys. We will be more than happy to continue the discussion. Thank you.